March 7, 1945, Remagen, Germany. Second Lieutenant Karl Timmermann led his company of the 27th Armored Infantry Battalion across the Lundorf Bridge, watching German engineers frantically working to destroy it beneath his feet. Explosions had already weakened the structure. Wires dangled from failed demolition attempts. The bridge swayed and groaned as his men ran across, expecting at any moment to plunge into the icy Rhine River below. Behind Timmermann, following his infantry across this miracle bridge that somehow still stood, came the engineers. Not to destroy, but to preserve. Within hours, they would be working under fire to repair damage, remove unexploded demolitions, and shore up weakened supports. And within days, just upstream and downstream from this captured bridge, other engineers would be constructing floating bridges capable of carrying entire armored divisions across Germany's greatest natural barrier. The story of how American combat engineers learned to build bridges faster than the enemy could destroy them is a story of innovation under fire, of mathematics meeting mud, and of ordinary soldiers performing extraordinary feats of construction while being shot at. It's the story of how the U.S. Army transformed military engineering from a specialized technical field into a rapid response capability that could keep pace with the fastest armored advances in history. The basic tactical problem of river crossing had challenged military commanders since ancient times. Rivers represented natural barriers that slowed or stopped advancing armies. A defended river crossing could tie up an attacking force for days or weeks. The defender held all the advantages: prepared positions, clear fields of fire, and the option to destroy bridges and force the attacker to cross under fire. By World War II, the problem had become more complex. Modern armies moved on wheels and tracks, not feet and hooves. A division advancing in 1944 required hundreds of trucks, dozens of tanks, artillery pieces, supply vehicles, and command cars. These forces couldn't swim across rivers. They needed bridges capable of supporting vehicles weighing 30, 40, even 50 tons. The German army, fighting on the defensive after 1943, understood this perfectly. Their doctrine emphasized destroying bridges as they retreated, forcing Allied forces to halt at every major river and construct crossings under fire. German engineers became experts in bridge demolition, placing charges that would drop entire spans into rivers, creating obstacles that should have required days or weeks to overcome. The U.S. Army Engineer Corps faced the challenge of keeping mobile warfare mobile. Armored divisions advancing across France in 1944 could cover 50 miles in a day on open roads. But a single destroyed bridge could stop that advance completely. Tanks couldn't swim, trucks couldn't ford deep water. The engineers had to provide crossing capability that matched the speed of the advance. Traditional military engineering focused on permanent or semi-permanent construction. Engineers built fortifications, roads, and bridges designed to last months or years. They worked methodically, with detailed plans and adequate materials. Speed was less important than durability and load capacity. The new challenge required a different approach. Engineers needed to throw bridges across rivers in hours rather than days. These bridges didn't need to last for years or even months. They needed to last long enough for an army to cross, perhaps a week or two. After that, permanent bridges could be constructed by follow-on forces. This shift from permanent to temporary construction seemed straightforward in theory. In practice, it required new equipment, new techniques, and a fundamentally different mindset among engineer troops. The traditional engineer was a craftsman who took pride in durability and precision. The combat engineer had to accept that good enough to get the job done was all that time and circumstances permitted. The U.S. Army began serious development of portable bridging equipment in the late 1930s. Early designs were cumbersome and slow to deploy. Steel pontoons were heavy and required cranes to position. Timber treadways took hours to assemble. The bridges that resulted could support heavy loads, but constructing them consumed time that mobile operations couldn't afford. The breakthrough came with the development of standardized modular bridging systems. Rather than custom designing each bridge for specific circumstances, engineers would use standard components that could be rapidly assembled in various configurations. A pontoon bridge across a narrow river might use 20 sections. A bridge across a wider river would use 40 sections, but the sections themselves were identical. This modularity solved multiple problems simultaneously. Training was simplified because engineers learned to assemble one type of section, rather than mastering multiple bridge designs. Logistics were simplified because supply officers needed to stock fewer different components. Repairs were simplified because damaged sections could be quickly replaced with identical spares. The M1940 pontoon bridge, later improved as the M1942 and M1943 models, became the standard U.S. Army tactical bridge. Each pontoon was a steel float about 15 feet long, 4 feet wide, and 3 feet deep. When partially flooded with water for ballast, a single pontoon could support about 15 tons. Multiple pontoons connected together with standardized treadway sections formed a floating bridge, capable of supporting the heaviest tanks. The beauty of the system was its flexibility. Engineers could construct infantry footbridges using minimal components or heavy equipment bridges by adding more pontoons. They could adjust to varying river widths and current speeds by modifying the spacing and anchoring. The same basic components served in dozens of different configurations. Training emphasized speed and standardization. Engineer companies drilled endlessly on bridge construction, timing themselves, competing against other companies, refining techniques to shave minutes off construction times. The goal was to make bridge building almost automatic, a series of practiced movements that could be executed under stress without requiring complex decision-making. By 1944, a well-trained engineer company could construct a 200-foot pontoon bridge capable of supporting 40-ton vehicles in approximately 4 hours under ideal conditions. This was revolutionary speed compared to traditional military engineering, but ideal conditions rarely existed in combat. The real test would be whether engineers could maintain that speed while being shelled, while working in darkness, while under direct fire from enemy positions on the opposite bank. Fort Beaver, Virginia served as the U.S. Army's primary engineer training center. The facility included river crossing sites where engineer companies practiced bridge construction in realistic conditions. Officers and NCOs learned not just how to build bridges, but how to organize work parties, distribute loads, maintain work pace under pressure, and troubleshoot problems that arose during construction. The training was deliberately stressful. Engineers worked at night simulating combat conditions. They constructed bridges while instructors fired blank ammunition and set off explosives to create realistic noise and confusion. They practiced recovering from simulated casualties, continuing work when key personnel were killed or wounded. One exercise involved constructing a bridge, then defending it while an opposing force attempted to destroy it with simulated demolitions. Engineers learned to position guards, establish perimeter security, and continue repair work while under attack. These lessons would prove invaluable in Europe, where newly constructed bridges became priority targets for German artillery and aircraft. The engineer companies trained alongside the infantry and armor units they would support. Combined exercises taught tankers to understand the capabilities and limitations of engineer bridges. Infantrymen learned how to provide security for engineer work parties. The integration of engineers into combined arms teams was as important as the technical bridge building skills. Individual engineer soldiers were cross-trained on multiple jobs. If the boat operator was killed, the pontoon handler needed to be able to take over. If the treadway crew took casualties, the anchor crew had to be able to step in. This redundancy in skills ensured that construction could continue even with significant casualties. The physical demands were immense. Engineer work required moving heavy steel components, often in water, frequently while exhausted. The Army selected physically robust soldiers for engineer units and conditioned them with training that was deliberately brutal. A soldier who couldn't handle the physical strain during training would collapse during actual combat operations when adrenaline and fear added to the physical load. Navigation and site selection received particular emphasis. Engineer officers learned to read maps and aerial photographs to identify suitable bridge sites. Not every location on a river was equally good. Engineers looked for straight sections with minimal current, firm banks that could support anchoring systems, and approaches that provided covered routes for troops and vehicles waiting to cross. The training also covered bridge demolition. Engineers needed to understand how bridges were destroyed so they could defend against demolition attempts and rapidly repair damage. They studied German demolition techniques, learned to recognize prepared charges, and practiced cutting wires and removing explosives under time pressure. By late 1943, the engineer companies deploying to Europe were arguably the best-trained combat engineers in the world. They understood their equipment intimately. They had drilled on bridge construction until the procedures were instinctive. They had been tested in realistic exercises that simulated the stress and confusion of combat. What they lacked was actual combat experience, and that would come soon enough. The D-Day landings in June 1944 didn't initially require major river crossings, but engineers faced challenges just as demanding. They had to clear beach obstacles under fire, construct causeways across flooded areas, repair damaged roads and bridges, and keep the invasion force supplied as it pushed inland. Engineer units landing at Utah Beach faced a landscape deliberately flooded by the Germans. The causeways connecting the beach to interior roads were choke points that could have trapped the invasion force. Engineers worked under sporadic artillery fire to reinforce these causeways, construct bypass routes, and keep vehicles moving inland. As Allied forces broke out of Normandy and began their rapid advance across France, the engineer units faced their first major river crossing challenges. The Seine River presented a significant obstacle in late August 1944. German forces had destroyed all the bridges in their retreat, leaving the river as a natural barrier that should have delayed the Allied advance for weeks. Engineer battalions reached the Seine on August 19th. By August 20th, the first pontoon bridges were under construction. The speed was remarkable. Engineers working around the clock constructed multiple bridges capable of supporting heavy equipment while German artillery intermittently shelled the crossing sites. The Seine crossings established patterns that would repeat across France, Belgium, and into Germany. Engineers would arrive at a destroyed bridge, conduct rapid reconnaissance to identify suitable pontoon bridge sites nearby, and begin construction often before the infantry had fully secured the far bank. The bridges went up in sections, with engineers working outward from both banks simultaneously, meeting in the middle hours later. Security was critical. Engineers working on bridge construction were vulnerable targets. German artillery forward observers prioritized bridge sites, calling fire missions that could kill engineers and damage partially constructed spans. Infantry units were assigned to provide close security, but the engineers themselves learned to keep weapons close and be ready to fight while working. The Moselle River crossing in September 1944 demonstrated how effective U.S. combat engineers had become. The Third Army's rapid advance had outrun supply lines and reached the Moselle with minimal bridging equipment on hand. Engineers improvised, using captured German pontoons supplemented with American treadways. They constructed a hodgepodge bridge that shouldn't have worked according to the technical manuals but successfully carried an armored division across the river. This improvisation became a hallmark of American engineer operations. When standard equipment wasn't available, engineers made do with whatever was at hand. They lashed together damaged pontoons that should have been discarded. They constructed temporary repairs using local materials. They kept bridges functional through sheer determination and creative problem-solving. The competition between construction and destruction became more intense as Allied forces approached Germany itself. German demolitions became more thorough. Retreating forces didn't just destroy bridges. They cratered approach roads, mined riverbanks, and positioned artillery to cover likely bridge sites. The engineers' 4-hour construction time under ideal conditions stretched to 8, 12, even 24 hours when working under sustained fire. Yet the bridges kept going up. For every bridge the Germans destroyed, American engineers built a replacement. The advance continued, sometimes slowed but never stopped completely. The mobile warfare that Patton, Bradley, and Montgomery demanded remained possible because engineers could bridge rivers faster than Germans could destroy the crossings. By March 1945, Allied forces had reached Germany's greatest natural barrier, the Rhine River. Wide, deep, and fast-flowing, the Rhine had protected Germany's western border for centuries. German forces had destroyed every bridge across the Rhine, preparing to make the Allies pay dearly for every crossing. Then came the miracle at Remagen. On March 7th, the 9th Armored Division discovered the Ludendorff Railroad Bridge still standing. German engineers had tried to destroy it, but their demolitions had failed. American forces seized the bridge in a chaotic assault and established a bridgehead on the far bank. The Remagen Bridge became the most valuable piece of real estate in Europe. Engineers swarmed over the damaged structure, working desperately to keep it functional. They removed unexploded German demolition charges. They reinforced weakened spans with timber supports. They constructed wooden treadways to supplement the damaged railroad deck. All this while German artillery pounded the bridge and German aircraft attacked it repeatedly. The bridge held for 10 days before finally collapsing on March 17. But in those 10 days, 5 American divisions crossed into Germany. And more importantly, engineers had used those 10 days to construct pontoon bridges upstream and downstream from the railroad bridge. When the Ludendorff Bridge collapsed, the pontoon bridges immediately took over its function without interruption to the advance. The tactical pontoon bridges at Remagen were engineering marvels. The Rhine at Remagen is over 1,000 feet wide with a current speed that can exceed 8 miles per hour. Constructing a floating bridge across such a river, under fire, was a task many engineers had privately considered impossible. Yet they did it, not once but 3 times, building parallel bridges to handle the traffic volume. The secret was organization and rehearsal. Engineer battalions had practiced Rhine crossings in training, using American rivers of comparable size. They had worked out procedures for anchoring pontoons in strong currents, for maintaining bridge alignment against river flow, and for reinforcing critical sections subject to maximum stress. The actual construction proceeded in carefully choreographed stages. First, reconnaissance teams surveyed the crossing site, measuring water depth, current speed, and riverbank characteristics. Then assault boats ferried infantry across to secure the far bank. Once the far bank was reasonably secure, engineers began positioning pontoons from both sides simultaneously. The pontoons were launched upstream of the intended bridge location, then guided into position by engineer boat crews. Heavy steel cables anchored to both banks prevented the pontoons from being swept away by the current. Treadway sections were positioned as each pair of pontoons was secured, creating a continuous roadway across the river. German artillery fire was intense. Shells falling near pontoons created waterspouts that threatened to swamp the floats. Direct hits destroyed pontoons, creating gaps in the partially completed bridge. Engineers kept spare pontoons ready, launching replacements immediately when sections were damaged. The work continued around the clock, with fresh crews replacing exhausted ones every few hours. The first Remagen pontoon bridge was completed in 32 hours, a remarkable achievement given the conditions. Within days, additional bridges were operational, including a heavy pontoon bridge capable of supporting the heaviest American tanks. Traffic across the Rhine became continuous, with vehicles crossing bumper to bumper while engineers made repairs and adjustments to keep the bridges functional. Other Rhine crossings followed Remagen. Patton's Third Army crossed at Oppenheim on March 22 to 23. Montgomery's 21st Army Group crossed near Wesel on March 23 to 24. In each case, engineers had pontoon bridges operational within 24 hours of the initial assault crossing. The Rhine, which should have been an insurmountable barrier, became merely another river, crossed and recrossed as Allied forces drove deeper into Germany. The engineering challenge wasn't just building bridges quickly. It was building them faster than the enemy could destroy them. This created a peculiar dynamic where construction speed became a tactical weapon. German forces quickly learned that conventional demolition timing didn't work against American engineers. If Germans waited until a bridge was heavily used before attempting demolition, American engineers could repair damage and have the bridge functional again within hours. If Germans attempted early demolition while the bridge was under construction, American engineers would simply modify the design and continue building. The solution, from the German perspective, was continuous interdiction. Rather than attempting single decisive demolitions, German artillery would shell bridge sites continuously, trying to inflict enough cumulative damage that repairs couldn't keep pace with destruction. This worked sometimes, forcing engineers to abandon sites and relocate to areas with less direct fire exposure. American engineers countered with dispersion and redundancy. Rather than concentrating on a single bridge, they would begin construction on 2 or 3 bridges simultaneously. German artillery could target one bridge, but not all of them at once. At least one bridge would usually be completed even if others were damaged or destroyed during construction. The engineers also developed techniques for rapid repair of damaged bridges. Damaged pontoons could be isolated and replaced without dismantling the entire bridge. Treadway sections holed by shell fragments could be quickly patched or replaced. The modular design that made construction fast also made repairs fast. Night construction became standard. Engineers learned to work in darkness, using minimal lighting to avoid giving German artillery easy aiming points. The work was more difficult at night, requiring more time and causing more accidents. But completed bridges were more likely to survive until daylight if German gunners couldn't see them during construction. Camouflage and deception played roles as well. Engineers would begin construction at one site while conducting obvious preparations at another site several hundred yards away. German artillery would often shell the decoy site while the real bridge was built elsewhere. Smoke screens obscured construction sites, though they also made the work more difficult for the engineers. The psychological dimension was significant. German forces fighting in the retreat through France and Germany faced a demoralizing reality. Nothing they did could stop the American advance for long. They could destroy every bridge, crater every road, and mine every approach. But within hours or days, American engineers would have everything repaired, and the advance would continue. This sense of inevitability affected German morale and combat effectiveness. Units that might have fought harder to hold defensive positions saw less point when they knew that even successful defense would only delay the inevitable by a few days. The engineers' success didn't just facilitate the American advance, it undermined German will to resist. The engineering accomplishment represented by World War II. Tactical bridging deserves recognition as one of the war's underappreciated technical achievements. The M1943 pontoon bridge system, in its final refined form, was a masterpiece of functional design. Each pontoon weighed about 1,200 pounds when empty, light enough that 4 men could maneuver it, heavy enough to provide stability when flooded with ballast water. The steel construction was robust enough to survive rough handling, yet thin enough to keep weight manageable. The design accommodated bullet holes and minor shell fragment damage without compromising flotation. The treadway sections connecting the pontoons were equally ingenious. Steel frames supported wooden decking that provided vehicle traction. The sections locked together with simple pin connections that could be engaged and disengaged without tools. Damaged sections could be removed and replaced in minutes. The anchoring system adapted to various riverbed conditions. On soft bottoms, large anchors buried in mud prevented bridges from being swept downstream. On rocky bottoms where anchors wouldn't dig in, engineers used deadweight anchors or ran cables to sturdy trees or structures on shore. The flexibility meant engineers could construct bridges in locations where riverbed conditions would have made traditional bridging impossible. Load capacity calculations were straightforward enough that any engineer lieutenant could perform them in the field. By knowing the number of pontoons, their spacing, and the current speed, engineers could determine maximum safe vehicle weight for any particular bridge configuration. This prevented overloading that might sink pontoons or snap treadway sections. The typical heavy pontoon bridge could support vehicles up to 50 tons at speeds around 5 miles per hour. This was adequate for any American vehicle, including the heaviest tanks. Engineers marked weight limits clearly at bridge approaches and assigned traffic controllers to enforce speed limits and vehicle spacing. Overload or excessive speed could set up destructive wave motion that might collapse an entire bridge. Maintenance was continuous. Engineer crews remained with bridges after construction, constantly adjusting pontoon ballast to maintain proper flotation, retightening connections loosened by traffic vibration, and replacing components damaged by use. A pontoon bridge was never really finished. It was always under construction, constantly being repaired and adjusted to keep it functional. The logistics supporting bridge operations were themselves impressive. Engineer supply columns carried hundreds of spare pontoons, thousands of feet of treadway sections, anchor cables, tools, and repair materials. When an engineer battalion moved forward with an advancing army, it brought along essentially a portable bridge factory capable of constructing multiple bridges without resupply. Behind the technical achievement were the engineer soldiers themselves. Ordinary men performing extraordinary work under impossible conditions. The physical demands alone were brutal. A pontoon weighing 1,200 pounds had to be lifted, carried, positioned in water, and secured, often while standing in cold water, frequently while exhausted, always under time pressure. Engineer casualties were significant. Working on bridges made men vulnerable to artillery, mortar, and small arms fire. An engineer standing on a partially completed bridge was an easy target, clearly visible, unable to take cover. Engineer companies crossing rivers in assault boats to secure far banks suffered casualties comparable to infantry. The psychological stress was different from but comparable to combat infantry. Engineers knew they were being targeted. They could hear shells coming, see impacts walking toward their position, but couldn't stop working. The mission demanded that construction continue regardless of danger. Men learned to keep working through artillery barrages, through fear, through exhaustion. recognition was often limited. While infantry and armor received public attention and medals, engineers worked in relative obscurity. Their achievements were measured in bridges built and roads repaired, unglamorous accomplishments that didn't make dramatic newspaper headlines. Yet commanders understood their value. Patton famously said his engineers were worth their weight in gold. The engineer companies developed strong unit cohesion. Men who had trained together, who had worked shoulder to shoulder building bridges under fire, formed bonds as strong as those in infantry units. They took professional pride in their work, competing informally to see which company could build bridges fastest, make the most creative repairs, or solve the most difficult problems. Individual heroism often went unrecorded. An engineer who continued working while wounded, keeping a bridge section from collapsing until it could be secured, might receive a Bronze Star if his officer happened to witness the action. More often, such acts were simply part of the job, expected behavior that didn't warrant special recognition. The engineers improvised constantly. When standard equipment wasn't available, they fabricated alternatives from whatever materials they could find. Captured German bridging equipment was incorporated into American bridges. Civilian boats and barges were commandeered and converted to military use. Buildings were demolished to provide timber for bridge reinforcement. Some engineer soldiers had civilian construction experience that proved invaluable. Carpenters, ironworkers, heavy equipment operators all brought skills that transferred directly to military engineering. The Army tried to identify men with relevant civilian experience and assign them to engineer units, though the demand for engineers eventually exceeded the supply of experienced construction workers. The majority of engineer soldiers were young men with no construction background who learned everything in training. They became competent bridge builders through repetition and necessity. The Army's training system, combined with good leadership and practical experience, transformed farm boys and city kids into capable military engineers in months. The combat engineering achievements of World War II established principles that remain relevant in modern military operations. The fundamental insight was that engineering isn't a specialty that supports combat operations. It's an integral part of combat operations. Mobility and engineering are inseparable in modern warfare. The modular, standardized approach to bridging equipment influenced post-war military engineering development. The U.S. Army's current tactical bridging systems are direct descendants of the World War II pontoon bridges, refined and improved but based on the same principles of modularity and rapid deployment. The emphasis on speed over permanence revolutionized military engineering doctrine. Modern combat engineers accept that temporary solutions deployed quickly are often more valuable than permanent solutions deployed slowly. This mindset applies to everything from bridge construction to runway repair to obstacle clearance. The integration of engineers into combined arms teams became standard practice. Modern combat brigades include organic engineer battalions that train and deploy with the same infantry and armor units they will support in combat. The World War II practice of attaching engineer companies to advancing divisions evolved into permanent organizational relationships. The World War II engineer experience also highlighted the importance of engineer reconnaissance and planning. Modern engineer officers receive extensive training in terrain analysis, site selection, and resource estimation. The ability to look at a river and quickly assess where and how to bridge it remains a critical skill. The human factors lessons were equally important. Engineer soldiers required different selection criteria and training than infantry. Physical strength and mechanical aptitude matter more than traditional combat skills, though engineers still must be capable fighters when necessary. Modern engineer training retains the physically demanding, technically focused character developed during World War II. The competition between destruction and construction that characterized World War II river crossings continues in modern conflicts. Adversaries study how to destroy bridges and disrupt logistics. Engineers study how to rapidly restore capability despite enemy action. It's an ongoing technological and tactical arms race that traces directly back to the European campaign of 1944-1945. Perhaps most importantly, World War II demonstrated that tactical engineering excellence can have strategic impact. The ability to maintain mobility despite destroyed infrastructure allowed Allied forces to conduct mobile warfare deep into Germany. What might have been a grinding, positional campaign bogged down at river lines instead became a fluid advance that collapsed German defenses in months rather than years. The The story of American combat engineers building bridges faster than the enemy could destroy them is ultimately a story about the intersection of training, equipment, and determination. The engineers succeeded because they had good equipment that was well designed for rapid deployment. They succeeded because they were thoroughly trained and knew their equipment intimately. And they succeeded because they had the courage and determination to keep working under fire, accepting casualties, continuing the mission regardless of conditions. In the broader narrative of World War II, combat engineers don't occupy the prominent place given to infantry, armor, or air power. Their contributions were less visible, less dramatic, less suitable for heroic storytelling. Yet their work was fundamental to Allied victory. Without engineers to bridge rivers, repair roads, and maintain mobility, the Allied advance would have stalled. The impressive operational tempo of 1944 to 1945, the rapid armored thrusts that characterized the campaign, were possible only because engineers kept the armies moving. The technical achievement of building pontoon bridges in hours rather than days was remarkable. The operational achievement of keeping those bridges functional under sustained enemy fire was even more impressive. But perhaps the most significant achievement was the transformation of military engineering from a specialized support function into a rapid response combat capability that could match the pace of the most aggressive operational tempo. The race between construction and destruction that played out across hundreds of rivers in France, Belgium, and Germany demonstrated a fundamental truth about modern warfare. Mobility is often more important than firepower. The ability to go where the enemy doesn't expect, to maintain operational tempo despite obstacles, to keep moving when the enemy assumes you must stop. These capabilities can be decisive even when forces are otherwise evenly matched. American combat engineers in World War II proved that construction could match or exceed destruction in speed and effectiveness. They built bridges faster than the enemy could blow them up. In doing so, they transformed tactical mobility into strategic advantage and demonstrated that in modern warfare, the shovel and the wrench can be as important as the rifle and the tank.